So what we looked at in our previous videos was looking at the force, the results of the magnetic field on a particle. Now we're going to be looking at the force of the magnetic field, but on a conductor. So if we're going to be looking at a conductor, we have to look at a couple different things. We have to look at the amount of current that's going through. And current, as a reminder, is measured in amps. We also have to look at the length. So the length in meter of the conductor. We also need to keep in mind the B, which is the strength of the magnetic field. And remember, that's in our new units of Teslas. And we need to make sure that the movement of the current, and then the magnetic field strength are 90 degrees away from each other. So sine of the angle. And that'll be important in this question that we have right here, because as you'll see, I gave you 3 different angles. Now, I don't need to really do this question 3 times. What I can do is I can say my formula is Fm is equal to ILB sine theta. And for all 3 of these examples, the current is 15, the length is 0.1, the B is 0.6, sine of the angle. So when I plug all these in, I end up with 0.9 sine of the angle. And this is where we can see how this can make a difference. So if I plug into here 0.9 times sine of the 90, well, that's just going to be equal to 1, which means my answer is 0.9 newtons. Here, if I've got 0.9 times sine 0, well, sine 0 is 0, which makes this 0 newtons. Here, I've got 0.9 times sine 90. Sine 45. And we're going to get a number between 0 and 0.9. And when we plug it into the calculator, we end up with an answer of 0.64 newtons.